Okay, it's already 2 p.m. It's time to begin our seminar today. And I have the honor to introduce our today's speaker, Professor Maciej Lewenstein. Maciej Lewenstein is a very well-known figure at CFT. Currently, he is a professor at the Institute of Photonic Sciences, ICFO, in Castelldefels in Catalonia, Spain. And he's a Polish theoretical physicist with deep connections with our institute. He's one of the world's leading specialists in quantum optics, physics of cold gases, and quantum physics in general. He did his Master of Science at Warsaw University under Professor Zążewski. After that, he worked at CFT for a couple of years. He then went on to obtain his PhD under Fizyki in 1983 with summa cum laude. Later, he moved out of Poland and worked in many places in Germany, Essen, Hanover, in the US, at Harvard University, University of Colorado Boulder, and also Service des photons, atomes et molécules of Centre d'études de Saclay in Paris, Saclay. He was for some time the collaborator of Roy Glauber, the Nobel Prize winner. He won himself a couple of awards, the Humboldt Prize. He also held the ERC Advanced Grant, and among many other awards, also the Foundation for Polish Science Prize in 2011. Apart from his scientific research, his interest also includes jazz music, and a few years back, he published an important book about Polish jazz recordings and beyond. But today he will talk more about photons. And I pass the mic to Professor Lewenstein.
Thank you very much, Mikołaj, and everybody who was involved in inviting me here. It was supposed to be a few weeks ago, but I have to cancel it because in the meantime I had an accident and broke my femur, so that was kind of complication. But anyway, and then today it turned out to be possible to use the open slot, and then I will tell you the same thing that I was supposed to tell you weeks ago. So as somebody, I think Mikołaj has already observed that I start always with all these logos of the organizations that used to finance my quantum optics group at ICFO. Unfortunately, this is a kind of record of the lost fortune, because most of these grants are finished and I have no money practically. I'm applying for the new ones. We will see what will happen. But the truth is that, yeah. But anyway, I still have this slide. It shows the good old times. And the title is Why Photons? And I try to prepare this talk as a colloquium, so general, but also kind of entertaining a little so that you have some fun. So subtitle is A Psychoanalytic Portrait of Scientist as a Mature Man. This is me, and I will describe you my drama of my relations to photons, in fact. Okay, this is the group that is at this moment. It used to be about 30 people. We collaborate with thousands of people all over the world, but at the moment in the group, there are not so many. There are some PhD students who are finishing, some Master of Science students that are also about to finish in a few months, one postdoc, and that's it. Okay, so the outline of the talk is I start with origins, so Maxwell theory and the reasons to quantize Maxwell theory. I will then go to quantum theory of optical coherence. I told you something about coherent states. So this will be a historical material that most of you know by heart, but anyway. For those who do not work on quantum optics, it will be, I hope, entertaining or educative at least. Then we will turn to strong field physics and do some historical introduction. And we talk about generation of quantum states in strong field physics, Schrödinger cat states in particular. And we will talk about three mechanisms to exhibit quantumness of strong electromagnetic fields. This will be the main subject actually of this talk. Okay, so let's go to origins. So some of you might go to the Bible, but we will go to the Bible of theoretical physics, which is Maxwell equations formulated by James Clerk Maxwell in the second half of 19th century. Here the Maxwell equations in SI units in a differential form. They describe electromagnetic fields as classical electromagnetic waves. There are 5 reasons that people usually name in order to that stimulate people to quantize electromagnetic fields. Usually the first one mentioned is photoelectric effect, theoretically described by Albert Einstein in 2005. So photoemission of electrons from metal plate accompanied by absorption of light quanta, photons. The name of photons comes from a chemist, Gilbert N. Lewis, who considered the term, coined the term photon in his letter, The Conservation of Photons to Nature, published much later in 1926. The second reason is Planck distribution law for blackbody radiation, formulated by Planck in the beginning of the 20th century. Here is Max Planck. So this is these are the curves which, if you calculate them using classical theory of electromagnetic fields, they diverge. But if you do the quantized theory of the photons, everything is finite and beautifully convergent and agrees with experiment. The next one is Compton effect, where the X-ray photon hits the electron and they both behave like particles, like billiard balls, more or less. This was discovered by Compton, who got the Nobel Prize for this discovery in 1927. Another one is spontaneous emission, theoretically described at best by Paul Audrin-Maria Dirac, where you have an atom before the process in the excited states. During the process, and the atom undergoes transition to the ground state, emitting photon of the energy corresponding to the transition frequency. And finally, maybe the most sophisticated reason are the vacuum fluctuations of the electromagnetic fields, which lead to the shifts of energy levels, in particular so-called lamp shifts discovered by Willis Lamp Jr. Here is Lamp Jr. And this is really a most important effect from point of view of supporting quantum electrodynamics, because this is really due to the fact that electromagnetic fields are quantum, described by quantum fields which fluctuate in the vacuum. Okay, are there 5 reasons or 4? And here my drama begins. So I have, when I was finishing Master of Science with my friend, now professor here at Centrum, Marek Kuś, we decided to do diplomas in, we both wanted to do mathematical physics, but it was not allowed at that time. So we went to the Zakład Elektrodynamiki Kwantowej i Statystyki i Fizyki Statystycznej profesora Iwo Biruli-Bielińskiego, and we both started to study then quantum optics, and our mentors, Kazimierz Żążewski and Krzysztof Wódkiewicz, the late Krzysztof Wódkiewicz, unfortunately, told us that quantum optics is nothing else but applied quantum electrodynamics, so applied quantum field theory. And it's non-perturbative and fascinating and so on. However, in the first lecture of our quantum optics theory course, they presented this paper by Willis Jump Jr. and Marlan Scully, the photoelectric effect without photons. So this is the paper in which, well, they solved the problem of photo effect using time-dependent perturbation theory in second order time-dependent perturbation theory and get the solution for the density matrix of the electron and get exactly the formulas of Einstein with the proper behavior of photo effect, but without quantizing the electromagnetic field. So their conclusion is we understand the photo effect as being the result of a classical field falling on a quantized atomic electron. The introduction of the photon concept is neither logically implied nor necessary for the explanation of the photoelectric effect. Okay, so photons betrayed me for the first time here, but not for the last time. So let's go now to the quantum theory of optical coherence, which in fact, this was the next subject we learned in the quantum optics theory course by Wódkiewicz and Zążewski. Here, this quantum optical coherence theory was stimulated by the astronomical observation of Hanbury-Brown twist effect in astronomy. And for the first time, maybe it was actually very well explained by classical fluctuations of electric fields by Emil Wolf and Leonard Mandel. Both of them are not with us anymore. But the true quantum electrodynamic explanation goes back to Roy Glauber and his quantum theory of optical coherence. I always put the name of George Sudarshan here, who did these discoveries in a sense independently at the same time. These are the famous papers by Glauber about photon correlation. The first one, which was now a few months ago, it had nearly 2,000 citations in Google. This is the one about quantum theory of optical coherence, where he formulates really this how to calculate correlation functions, so nearly 6,000 citations. And this is the most important one, maybe, where he introduced the concept of coherent states. So this one has nearly 10,000 citations. And the reason why Glauber got the Nobel Prize and not Sudarshan is exactly that the papers by Glauber were written in a very beautiful manner, very easy, and even though they being very rigorous, they were understandable for experimentalists, and that's why his impact on the quantum optics was amazingly bigger than others. Okay, so let's talk about coherent states. In quantum physics, the coherent states are the quantum states of the quantum states of harmonic oscillator are the most classical, if you wish, states of electromagnetic fields. So electric fields in those states oscillates like in the single harmonic oscillator. But these are quantum states, so obviously they exhibit quantum fluctuations, and this is represented in this figure. However, as the amplitude of the coherent state increases, the relative role of quantum fluctuations becomes less and less important, smaller, less important. And this is also illustrated here. We increase the amplitude here, and the relative role of fluctuation is negligible. So again, I feel betrayed by photons again, but this time in the context of strong fields. Why do we need photons if in the strong fields looks like we do not? Okay, so I remind you, quantum mechanical definition of the coherent state, which most of the students should know by heart. The probability of detecting n photons in a coherent state of amplitude alpha is given by Poissonian distribution, which is peaked at the average value of n, which is proportional to modulus alpha squared, and its variance squared is also alpha squared. So its variance, so square root of variance squared goes like square root of n, so it's much, much smaller than n in the limit when n goes to infinity. Again, I feel betrayed by coherence, by strong field states, because the role of quantum fluctuations in those states are negligible. Of course, in the 90s, there were another kind of quantum state introduced to quantum optics. At that time, mostly they were considered in the case of not too many photons, but so amplitude small. But anyway, these were so-called squeezed coherent states. So normally, each state of harmonic oscillator is characterized by the variance of the, in case of harmonic oscillator, position and momentum. In case of electromagnetic fields, this will be quadratures of electric fields, so the part which fluctuates like sinus or like cosinus, and they fulfill in appropriate units uncertainty relation. Delta x, delta y is bigger than 1/4. In coherent state, they are both equal and equal to 1/2. However, in the squeeze states, they are indeed squeezed. So the states are asymmetric. The delta x is different from delta y. The product is still 1/4. They minimize the uncertainty principle. But their Wigner function, which is a kind of quasi-probability distribution of these quadratures, is a nice Gaussian function, but is squeezed indeed. And the states, at least for not too large numbers of photons on average, were observed already in the 80s. Nowadays, there's a big progress and we can observe bright squeeze states. I will come back to this later. Okay, this is exactly the Wigner phase space distribution. When I went to Harvard in 1986, 87, Glauber had the grant from Navy because Navy was interested if the squeeze states can be used for something useful. And in particular, Glauber had the idea that to study the media, photons in media, because in the medium, if you look at the Maxwell equation in the medium, you see that what was originally creation and annihilation operator in the vacuum, in the medium mix, okay? So there is a mixture between these two operators, and this looks like squeezing, but it is not squeezing. It's simply, and this is what we have formulated in this paper, Quantum Optics of the Electric Media. Simply the definition of the photon is more complicated in the medium, but medium itself, if it's static, doesn't lead to squeezing. If it's dynamical, it can. So we were studying this in this paper, and this was kind of became a kind of reference paper of the description of photons in the media and allowed them to understand better squeezing phenomena in the media. So when I talk about squeezing, I have to mention these people. Squeezing came to great popularity, of course, in the context of gravitational waves. So the Nobel Prize for Gravitational Waves was given to Rainer Weiss, who unfortunately passed away a few years ago, and Barish and Kip Thorne. This was for LIGO detection of gravitational waves in the presence of colliding black holes. However, one should mention at this context the Nobel Prize for binary pulsars to Russell Holtz and Joseph Taylor which also was indirect proof of existence of gravitational wave. But first of all, we should mention Andrzej Trautmann, who unfortunately left us this year. Andrzej Trautmann was the first theoretician who, you have to remember that Einstein, even though he was the first to talk about gravitational waves, he didn't believe in them. He thinks they cannot exist, they cannot propagate. It was Trautmann who really proved that they should exist and propagate in a stable way. So this was really very important contribution of Andrzej Trautmann, of the Nobel category, I would say. Okay, in this occasion, it's worth to say that LIGO has surpassed quantum limit. LIGO is now using squeeze states in the detection. Squeeze states by factor more or less 3 in each of the variances. So if you see it in three-dimensional space, it's like increasing the volume in which you can observe the phenomenon by factor 3 times 3 times 3, so 27. So it's a non-trivial increase. This goes back to pioneering experiments of another guy who left us recently, a friend of mine, Jeff Kimball, who died in September 24. I have to mention here also Dick Slasher, who was an absolutely pioneering contributor to the squeeze states. Okay, so let's go now to strong field physics and see what can we do there. So in the beginning, strong field physics was the physics of multi-photon processes. Lasers were not so strong and not so coherent. So the typical theory was high-order perturbation theory. So matter and light were treated quantum mechanically. But with the advent of high-power lasers, particularly the discovery of the so-called chirped pulse amplification, which was awarded Nobel Prize in 2018, the need for quantum electrodynamic description of electromagnetic fields has diminished for the same reason that I mentioned with coherent states or bright squeeze states. So contemporary atto-science, or more generally ultra-fast laser physics, does not commonly employs classical description of electromagnetic fields while maintaining a fully quantum description of matter. Okay, so I feel betrayed by photons again, permanently. Okay, this is the Nobel Prize for ultra-strong lasers. Arthur Ashkin got it for optical tweezers, so something else, but very important anyway. And unfortunately, he passed away too. But Gerard Mourou and Donna Strickland got it exactly for the chirped pulse amplification. So for creation of the tabletop ultra-strong lasers that can go to intensities even 10 to 19 watt per square centimeters on the optical table. I mean, usually in processes I'm going to talk, we will go to 10 to 15, 10 to 16 watt per centimeter squared. So this is the Nobel Prize for atto-science that was given to Pierre Agostini, Ferenc Krauss, and Dan Lullier. And perhaps the most important process in atto-science is high harmonic generation, which is a process in which you so the process is like that you shine the laser pulse, strong and coherent, on the target, whatever the target is, atoms, molecules, solid state, even strongly correlated material. And then and the target produces photons or radiation, let's say. And this radiation has frequencies which are multiples of the driving frequency. So these are these famous harmonics. And they can be very high harmonics. So they go to harmonic number 100. So you can reach even the XUV part of the spectrum with this high harmonic generation process. And then you measure them and detect them, okay? And the mechanism of this process is the following. You electron in the atom, under the influence of strong electric field, feels this kind of tilted potential of electric field, and therefore can tunnel out from the nucleus to the outside of to the continuum, if you wish. And in the continuum, however, it still is under influence of very strong laser fields, and therefore moves with the laser field. In particular one, he moves away and comes back to the parent nucleus, being accelerated. And at the end of this process, it recombines to the parent nucleus, producing a high energy photon. This is more or less mechanism of the high harmonic generation. It's called three-step model. It goes back to Paul Corkum, who has formulated it in the context of plasma analogy. Independently, it was formulated by Ken Kullander, Ken Sheffer, and Jeff Krause in this, more or less in the same time. And by us together, or by me and my collaborators, better to say, in this paper, Theory of High Harmonic Generation of Low Frequency Laser Fields, which really is a fully quantum, at least from the matter point of view, theory of three-step model. This is Kullander, unfortunately, again, passed away last year. Sorry, 2 years ago already. Paul Corkum, he was the winner of Wolf Prize in 2023, I guess. And I put here the photo of Joe Weberly for two reasons. He passed away also, which is very sad, but he was a great friend of Warsaw quantum optics, of Polish quantum optics in general, and of the Center for Theoretical Physics in general. He has contributed very much to center contacts with the world, and also contacts of Institute of Physics with the world. So we really owe him a lot in Poland. Okay, so this is a paper of us, quantum three-step model, so to say. It has a lot of citations because it was even nominated to be the most cited paper at some anniversary, I don't know, 50 years of Phys-Reveil or something, or 25, I don't remember. Anyway, so why photons? Because from all these comments, we learned that we don't really need quantum electrodynamic description. In atto-science, fields are strong, and why photons? And then I have to tell you that there are three mechanisms to exhibit quantumness of electromagnetic fields, and this will be the main subject now of my talk. Classical description of electromagnetic fields is not sufficient in these cases. And the first one is due to conditioning. So this is a process in which we generate optical Schrödinger cat states of electromagnetic fields in intense laser matter interactions by using conditioning. So the idea is we put the laser field on the target, atoms, molecules, whatever you want. It undergoes interaction with the target. So coherent state undergoes certain changes. And then we condition this changed coherent state on the generation of harmonics and on the change of the amplitude of this initial state. And the effective, what we get in effect in a kind of caricature is a superposition of two macroscopically different coherent states, which is a Schrödinger cat state. So here is a Wigner function of such state. If you don't do conditioning, coherent states remain in a sense coherent. It's a beautiful symmetric Gaussian as a Wigner function. But if we do it, we have a Wigner function with negative parts and things like that. Okay, the second this is since we talk about Schrödinger cats, which are usually dead and alive, I prefer my modified cats, which are either alive or very much alive. The second mechanism that can lead to quantumness is quantum state engineering. Sorry, I tell you still about this conditioning. Conditioning is a very complicated process. This is the paper that we published few years ago after the first observation, where we really in very strong detail discuss the conditioning, the experiment, how can we condition on this intensity changes and things like that. It's quite complicated and very open process in the sense that you can condition in different ways. You can, for instance, the intensity which you measure at the end, you can demand that is smaller than a center value, or you can demand that is between certain values, the minimum and maximum, and so on. So all these kind of conditionings lead to different final quantum states. And in principle, you can optimize it. We haven't done it. We want to do it in the future. Okay. Another method to reach the to do another way of quantumness is to no, sorry, I still have conditioning. This is application of this conditioned ground state in nonlinear optics. I forgot about this. But yes, you can apply this. So this is you take a cat state, you put it on nonlinear crystal, you double frequency of it. You have two cats then, and then you superimpose one with another, and you measure multi-time correlation functions of the two. And in this way, you characterize quantumness of the cat, which is nice. Okay, and it also you can use this coherent Schrödinger cats for metrological applications, in this case for measurement of the phase in the beam splitter or something like that. Anyway, another nonlinear effects that can induce quantum effects are the effects induced by depletion of interband transition. So this is the second way. Here we don't do any conditioning. We look at the dipole correlation in the process. And typically when the depletion is not so small. And if we do this, this was in particular pioneered also by Misha Ivanov, who proposed to enhance this kind of effect by putting by doing harmonic generation in a resonant medium, where the harmonics are generated and then absorbed by the medium because they are resonant, and therefore that leads to nonlinear effects. In our case, we just go beyond and this is the effect. We go beyond the small depletion effects, and this is also something that has been observed in experiments, in particular these experiments by Jens Bigert and Hamed Merji, where they observed indeed photon squeezing, photon super branching correlations, and also photon entanglement by looking at the so-called violation of the Cauchy-Schwarz inequality. So this is also observed in the experiments. There are newer experiments with by Hamed Merji, where they even observe the squeezed correlations between the different harmonics. This is all harmonics from the solid state, not so high, 357, but still it's very fascinating experiment. And finally, I mentioned that nowadays you can produce squeezed states which are very bright. In particular, Maria Czechova from Erlangen is able to produce squeezed states of bright squeezed light, which can lead to interesting quantum generation of quantum high harmonics. You can also produce bright squeezed states with a strong coherent component, and people are also going in that direction. Pioneers here are the people from Technion, Ido Kaminer, Michael Kruger, Oren Cohen. And this is the paper that they published in Nature Physics. No, that was theories. We also have a paper on the subject where we propose the following theoretical experiment, theoretical project. We study the high harmonic generation in the circularly polarized light, in which classically the harmonic generation is totally forbidden. But if we use the squeezed light with quantum fluctuations, the generation becomes possible and in fact quite efficient. These are the spectra that you get in this layers. And all of this has to do with what I call Serfal process, and because we really study here how in the medium in which we have medium and photons, we study the really interplay between light and matter, how the light depends on matter and matter depends on light. So far in atom science, this kind of experiment has been done in matter simply. So by looking at the processes of entangled of quantum correlation between the electron and parent ion in ionization of two electrons in double ionization and so on, so on. Here, we will look at the entangled between the matter and light in the future. Well, we have some predictions but for the future. Okay, the conclusions are enjoy physics and beyond, and I have to, after all this, what I said, I have to reflect my relationships with photons, go back to my psychoanalyst, and reconcile with the photons. I thought so, really, when I gave this talk for the first time, and then I learned about a new paper by Iwo Białowieski-Birula and Zofia Białowieska-Birula, uncertainty relations in classical quantum theories of electromagnetism. So I read this paper, and this is a postscript on my talk. And Ivo writes in the end of his seminar that he gave a few weeks ago here, in a book on quantum mechanics, we read, uncertainty inequalities are intrinsic properties of quantum description of any system. I hope that I gave convincing arguments that uncertainty relation may appear wherever there are two competing descriptions of the same systems. The quantum nature of the system does not play the key role. So again, I'm betrayed by the photons, but even in a deeper way and more general way. So thank you, Ivo and Zofia. I have to go to my psychoanalyst again.
Thank you very much for a very nice talk. Now it's time for questions, and I think we have something like 15 or 20 minutes for that. So please raise your hand if you want to ask a question or type it in the chat. At the moment, I don't see. And oh, there's Michał Matuszewski. Please go on.
So if I can ask a question. So I was wondering about these conditions cut states, so that appear in attosecond processes. So I understand that this conditioning is somehow related to post-selection in some way, but
Yes.
Is the quantum non-classicality actually appears already before this conditioning, or is it kind of induced by this conditioning? So
I mean, okay, strictly, I mean, there are two ways of looking at this. And there is a simplified way of describing the state, and you may say coherent state when it's strong and depletion if small remains coherent. There is nothing quantum there. But the truth is, it's not completely truth, because of course there is a conservation law in the process of interaction which conserves the number of photons. So whatever in the coherent state you have n photons, and whatever you produce the harmonics, they are correlated. And this is a correlated that is essential for, so to say, creating the scat in the observation. So if you just are too trivial, we were like that at the beginning. We were doing this naive picture and we are guessing, educated guess for the final state. And we were very lucky guessing it correctly. But the truth is, it's a very complicated process in which this correlation due to conservation law are dominant, are absolutely important. So you need, if you want to do it correctly, which we have done in the old days with the phenomenological theory where the time dependence of the electromagnetic fields were introduced by, phenomenologically, the spectrum was discrete for the harmonics and things like that. If you want to do it really properly, you have to do the fully quantum theoretical description of the system in which the conservation law is included automatically. I mean, the Hamiltonian is time independent and the photons or the energy of the photons is conserved. Whereas in our case, we have been putting it by hand. Yeah, which is okay, but it's phenomenology. It's not elegant, let's say. But to do it really in a full quantum electromagnetic picture is very difficult technically. To some extent boring. I don't think it's boring. It's interesting, at least for a student. But it's challenging.
Okay, Krzysztof Pawłowski.
Thank you, Cześć, for the talk. I have again a question on this about this cat state. So because you have shown this Wigner function, I guess, which was quite distorted. So the question is, do you think you can reach very nice big Schrödinger cat state with this method, or it will be really limited? Because it was not so nice as in Serge Harosh pictures, yes?
No, it was not. No.
But
So evidently,
some...
the main thing is that essentially, if I make this educated guess, or I would say caricature of the states that we generate, the states is a superposition of the coherent state that was initially and the coherent state that was changed by the interaction, but projected out. So if they differ nothing, there is nothing. If they differ too much, they are practically orthogonal, like in Harosh's thing. But projecting out doesn't mean anything because they are orthogonal. So the point is to have states which differ macroscopically, but not too much. Okay, so that means that they have to have overlap, which is non-trivial. And this is what gives them this kind of, you say, not so nice Wigner function. On the other hand, it gives also robustness, because if you think about robustness with respect to measurement, Harosh, this parity Schrödinger cats, if you measure one side, they immediately collapse to the one side. Ours not, because they are kind of dirty.
Okay, I see.
So there are advantages, as always. There are always advantages. And of course, disadvantages.
Okay, thank you.
Thank you. We are waiting for the third question. I don't see any, so maybe I will ask my question. I'm a completely new person to this whole field, but I noticed that in your talk, when you talk about photons, you never pretty much referred to polarization or anything that follow from the polarization, like Berry phase. Have you ever had to use any of these notions, or are your photons polarizationless?
Yeah, I mean, most of the processes I was talking about, the simplest one in this high harmonic generation, were corresponding to the situation where the electric field is polarized in a given direction and everything, so to say, happens in this single polarization direction. But of course, polarization play a very strong, important role, and you can use it in these processes and so on. I mean, I didn't talk about it, but yes, it adds a lot of richness. And yeah. In particular, we are trying to study now the possibility of generating, when you play with polarizations and also with the angular momentum of the light, you can create the states that already in the electric field that you generate have some topological non-trivial structures, like, for instance, how do you call it? Something that is really bending around, knotting around, or things like that. So if you apply this kind of field to the medium, what will you get if you condition in the Schrödinger cat, or even without conditioning in this other process in which you use the nonlinear effects? Will you get something that is also topological or at least geometrical? This we don't know. We try to study it, but there, of course, polarization plays an absolutely important role. So the simplest way is to take a elliptically polarized field and see how the reaction of my medium change with the ellipticity of the field and the position of this ellipse, which is a kind of angle. And do I see it on the other side when I condition appropriately? I don't know. But it's one of the questions that people are trying to ask and answer.
Thank you. Are there more questions to Maciej? Okay, I don't see any, so I think it's time to wrap up. Let's thank our speaker again. And it was very nice to listen to your talk. And I hope we'll see you at CFT at some point, Maciej.
I hope so.
Thank you very much. Yeah. Also, thank you very much, Juan and Arkadiusz, for basically taking care of the technicalities of the recording.
Okay.
I think we can end the session now.
Thank you very much, everybody.
Thank you.
Bye-bye.